session of the what geochemistry tells us. So as first presenter, we have Orlando Vaselli from the University of Florence. He's also the president of the Italian Geochemical Society, which is one of the patronage that we have for this webinar. So the microphones are muted, and after the presentation, they will be unmuted for any questions that you have. Orlando,
okay.
please lead.
You disable the screen sharing.
Yeah, 1 second. Now it works.
Okay, can you see the slides? Yeah. Okay. Okay, so thank you very much to Arthur and the colleagues of the Cluj University. And so this talk is going to show some evidence about the sampling of gases and water, basically pointed out how can do a good sampling for stable isotope analysis. Basically, what we need to do is to avoid as much as possible, let's say minimize any isotopic fractionation, because as you know, stable isotopes has these strong problematics related to the isotopic fractionation. So the main types of phases that we are going to deal with are gases and waters. So we will see different types of sampling for the stable isotopes in these two phases. So, as you know, when we are dealing with isotopes, we are expecting to use ratios. When we are dealing with the radiogenic isotopes, the referred ratios are, for example, the radiogenic isotope divided by the stable isotope, strontium 87 divided by strontium 86, and so forth. Differently, for stable isotope, the used ratios are considering the less abundant isotope divided by the most abundant isotopes. And basically, the typical example is the oxygen 18 divided by oxygen 16. The point related to the stable isotopes is that the isotopic fractionation is a very small, it's very tiny, very difficult to be recognized even by mass spectrometry. For this reason, we use the typical delta notation that all of you know about it. So we use the measured ratio by mass spectrometry divided the reference standard. Usually could be seawater, could be air, could be different other standards. In these two pictures, you can see which are the ratios that we may try to analyze in the gas and the water phases. Obviously, due to the reason of time, we are not going to be able to deal with all these ratios. So we'll see just a few of them. Obviously, we are going to see the most important ones. So first of all, we start with the gases. And as you know, we have different kind of gases. We have an atmosphere, we have our bubble, our atmosphere with a lot of nitrogen, with a lot of oxygen, some argon and other gases, very few carbon dioxide. This means that when we are doing the sampling, we must avoid any contamination by our bubble, by our atmosphere. Because we have different kind of gases. We have methane-rich gases, typically found, for example, in the mud volcanoes, the so-called sedimentary volcanoes. We also have a lot of CO2-rich gases. Basically, these are also called dry gas vents. We also have, very rarely, nitrogen-rich gases. So we have a large variety of different gases. And we will start with the most complicated stuff that are the volcanic gases. Because usually the gases I was talking about a few seconds ago are mostly characterized by low temperature. When we are dealing with volcanic gases, as shown in this case, we may have fumaroles that may reach very high temperature. This is a fumarole in Satsuma, Hiroshima volcano, where the temperature is 815 degrees. And we have a very large variety of temperature for 70 degrees up to 900 degrees. This is very important for the sampling related to the stable isotopes. Obviously, it's important also for the sampling of the gas chemistry. Why we do study volcanic gases? Because they play a fundamental role in forcing the magma to rise. And moreover, they convert thermal energy into mechanical energy. This means that the higher is the content of gases in a certain magma, more dangerous could be the eruption. Before we were talking about the Etna. Etna is producing lava fountaining, basically because the amount of gases are not that big. If we are going to have an eruption at Vesuvius or in other subduction-related volcanoes, we may expect much larger eruption and much more dangerous. The other point is that when we are studying the volcanic gases, we are also expecting to have variation at the surface of these gases. This means that the chemical composition may be varying over time due to the status of a certain volcanoes. This means that the variation that we have at the emergence point may reflect what is going to happen down to inside the volcano. Why stable isotopes? Because they may give important hints on the source of the gas compounds and may allow to understand the meaning of their variability in time. This means that the isotopic ratio, the stable isotopic ratio are not constant, may be varying with time. And this is important because it may allow us to understand what is going on in a certain volcanic system. What do we mean with the volcanic gases? Basically, they are very important because they contain the same ingredients that have generated the secondary Earth's atmosphere. So basically, are important for those researchers who are studying the evolution of our atmosphere. On the other side, volcanic gases is related to a very general term. We have different kinds of volcanic gases, as we will see. And this is important also for the sampling of these gases, and particularly for the stable isotope. It's a generic term that is used to indicate a spontaneous exhalation phenomena associated with the presence of volcanic edifice. The other most important point is that the volcanic gases are multi-component and multi-source hot fluids emitted in a spatial and temporal association with volcanic system. What does it mean? It means that what we are going to get at the surface may not be representing of the original, of the pristine magmatic gases, because as the magmatic gases is rising up to the surface, secondary processes may occur, hydrothermal system, for example, or secondary processes related to water, rock, and gas interactions. So what we get at the surface could be something completely different with respect to what is emitted from a magma. In this respect, we have a large variety, as I said before, a large variety of emission. Fumaroles are the most typical and most spectacular manifestation that we have in a volcano, other than the eruption itself. We also have a steaming ground. Fumarolic are just a sort of spot. They are related to fractures. Steaming ground is a surface usually at the temperature, as the name says, steaming, at the temperature of 100 degrees, at the temperature of the boiling water, basically. Other than this, we have a boiling pool, as there are quite several beautiful examples in Italy, as in the Azore Islands, for example. Or we have bubbling pool. The difference basically is the temperature. Bubbling pool are usually very low in temperature, 20, 30, 50 degrees. Boiling temperature, we are up to 100 degrees. Then we have crater lakes. This is an example from Poas, where you have the fumaroles that are interacting with a water body, like a lake. Then we have the geyser, another beautiful example, typical of Yellowstone and Iceland. We have also, very rarely in volcanic environment, mud volcanoes. Finally, we have two other examples that are the gases associated to thermal waters. Here we are at the Dallol in Ethiopia. On the other side, we also have dry gas bands. Dry gas bands because the temperature is low, because it's carbon dioxide dominating this manifestation. And as you know, carbon dioxide is a cold gas. So basically, there is no steam. Finally, the other manifestation that you may have is something that is hidden. You don't see any evidence of bubbling or boiling. Just you may realize that there is something going on because there is no vegetation. This is typical when you have a lot of CO2 that is called diffuse soil, the gassing. And these manifestations do not allow the vegetation to be growing. So let's have a look at the main component in the volcanic gases, and then we start with the stable isotopes. Here there is a long list. I mean, with Franco Tassi, we analyze 150 gas compounds in the fumaroles. This means that all these gases cannot be related to one source. There must be different sources that are basically affecting what we are going to collect at the surface. But we have some important points. First of all, we have steam. That is the most important compounds. Maybe in the volcanic gases, maybe reach 99%. Then we have what are called the acidic gases, SO2, HTS, hydrofluoric and hydrochloric acid, and CO2. Among these acidic gases, we have SO2 and the hydrochloric and hydrofluoric acid that are the so-called magmatic triplet. What does it mean? It means that when you have SO2, it means that the magma, I mean the gas related to the magma, are reaching the surface. Okay, there are less secondary processes that are affecting the uprising magmatic gases. So the fact that we have a lot of these gases is important to understand which is the source. And in these cases, you need to apply isotopes. And Giggenbach, in one of the most famous geochemists in the late 80s, did a sort of a classification for volcanic gases. He calls essential those isotopes related, for example, to the steam, delta 18 and delta deuterium, to understand the source of water, because we have different sources. Delta 13 of CO2, because CO2 may be atmospheric, maybe thermometamorphic, maybe magmatic, maybe biogenic, different sources. So the isotopic signature is important. We have helium 3, helium 4 ratio. Helium 3, helium 4 is a little bit, is not a very stable isotopic ratio, because as you know, helium 4 is related to the radioactive decay of uranium and thorium. So even this ratio is important because helium 3 is mostly considered a pristine degassing gas from the deepest part of the Earth, whereas helium 4 is a most superficial gas because it's related to two incompatible elements such as uranium and thorium. Then there are a group that is called very useful, tritium in water. We are not going to deal with this, but it's important to try to understand how long is the circulation of the steam inside the volcanic system. Most important, we'll see how to do this, the delta 34 sulfur in H2S and SO2 to understand if, for example, they are in equilibrium between them or they are in disequilibrium. Finally, there are useful isotopes such as delta 13, delta deuterium in methane, delta deuterium in molecular hydrogen, delta 15 nitrogen in molecular nitrogen, argon, and so forth. I mean, it depends how much money you have to do all the list of the isotopes that are possible to be done. So how do we do this collection? How do we collect a good sample for chemistry and for isotopic analysis? This is a typical geometry that we use in our department. Basically, we have a titanium tube, and then we have these sort of coaxial tubes that are called dewars. They are coaxial tubes that are separated by vacuum. So this means that the gas as uprises and enter inside this dewar system, there is no loss of heat. This means that the composition that you have at the final part of this dewar system is the same of inside the fumarole. This to avoid any, for example, condensation problem. We use titanium tubes when we are dealing with high temperature, because if you, in the past, they were using to use iron tubes, but you can see by this reaction, the reaction between iron and water and acids, as they are present in the fumarole gases, produce hydrogen, and hydrogen is a typical gas that you may find in fumaroles. So titanium is the perfect metal that can be used for this sampling for temperature up to 650 degrees, because for higher temperature, you have the same reaction as we have seen for iron. Basically, you have the release of hydrogen, and we do not want this. This means that when you have higher temperature, let's say 800, 900, they are very rare, but there are fumaroles with this high temperature, you need to use quartz tubes that are very expensive, they are very fragile, and you must be very, very careful. So what is this part? In the final part of this geometry, we have a gas vial. It's an important gas vial because it's a one-way gas vial, where in the laboratory we used to add about 20 mils of a very alkaline solution, 5 molar sodium hydroxide, at which we add a suspension of 0.15 molar of cadmium hydroxide. Because we are adding this cadmium, because cadmium basically is going to trap the sulfur related to H2S to form cadmium sulfide. And this, you can see the color, the difference in color between the pre-sampling gas vial and the post-sampling gas vial. Basically, the yellow color is related to the presence of H2S that react with cadmium to form cadmium sulfide. And it's important that we need to separate H2S from SO2. And you can see here the reaction. I'm not going through all the reaction because it would be very boring, but all the acidic gases are going to react with the sodium hydroxide to form basically ions. From a gas phase, we pass into a solution phase. So CO2 is producing carbonate, and look at SO2 and H2S. You see that they have the same product. So this means that I could not do the isotope of SO2 and H2S because here they may be producing the same product. So we need something to separate these phases, and this is the reason why we are going to add cadmium. These are for the acidic gases. Then we have the so-called uncondensable gases, hydrogen, methane, nitrogen, all the noble gases, hydrocarbons, because they do not react with the alkaline solution, and basically they tend to be enriched in the headspace of this gas vial. Basically, this is important because you have an enrichment, a sort of pre-concentration of these gases that are in very, very low amount. Keep in mind that the water and the acidic gases may be up to 99% and more in fumarolic gases. So this pre-concentration is important even for the stable isotopes. Then we have carbon monoxide that is quite tricky because carbon monoxide tends to react with alkaline solution, is a time-dependent reaction to form formiate. Finally, we have the steam that tend to condensate. So we have the phase, the gaseous phase to the liquid phase. So let's start with the steam. The steam isotopes are important because may allow us to define the source of the water. We may have magmatic water, we may have andesitic water, we may have hydrothermal waters, different sources of waters. It's important to have the isotopic composition of the steam. And the other point is that since we are going to have very high temperature, we need to avoid the isotopic fractionation, particularly of hydrogen, because the mass differences between hydrogen 1 and hydrogen 2 is 100. So the isotopic fractionation is very strong. So we use this sort of equipment. We call it the snake, basically, because you see there are a lot of tubing. But the most important thing is that here you have the titanium tube, you have the dual tubes, and here you have this stuff that is called Graham condenser. Basically, the gas flux enter inside this cooling serpentine, and the cooling serpentine basically is continually in contact with fresh water, with cold water. So basically, the temperature drop down, and this avoid any isotopic fractionation of the stable isotope of water. And this condensation has two important points. The first one is that you have a condensate where you can do basically the hydrogen and the oxygen isotope in the steam. The second point is that you may collect what is called the dry gas, because since you have a drop in the temperature, you may collect the dry gas, all those gases where the water has been cancelled, removed totally. And why this is important? Usually you have a drop of down to 30 degrees. This allows us to minimize the isotopic fractionation. But the other point is that you see that the gas flow inside the condenser. Here is a slightly different condenser with respect to the previous one. But the important point is that here you have the drop of waters that condense, and with the condensation, you also have the removal, or let's say the scrubbing, for example, of the most acidic gases, such as SO2, hydrochloric and hydrofluoric acids. So the gas flow, once the water has been removed, you may collect the dry gas. You collect the dry gas with a two-way gas vial. You have two ends of this gas vial. So you may flash continuously this gas vial until you are sure that basically you are collecting just the fumarolic gases without water. And what we can do in this dry gas, we can do a lot of things. We can do the helium isotopes, the argon isotope, the nitrogen isotope, the carbon isotopes in CO2 and the carbon isotope in methane, even obviously the oxygen and hydrogen in these two carbon compounds. In the condensate, we do obviously the oxygen and the hydrogen isotopes, but also we can do other analyses that are quite important, such as boric acid and ammonia, basically, that being in a liquid phase, we are going to measure ammonium. So basically, with this one single equipment, whose geometry is represented here, you can do a lot of things. Gas chemistry and isotope, stable isotope. The point is inside the gas vial when you go back to the lab. Because in the gas vial, you have the uncondensable gases that are occupying the headspace, so the noble gases and hydrocarbons and so forth. And then you have a liquid phase, that phase where the acidic gas is dissolved. And then you also have a solid phase related to the cadmium sulfide due to reaction of the hydroxide, cadmium hydroxide with H2S. So you can do all the analysis, gas, ion chromatography, potentiometry, molecular spectrophotometry, whatever you want. But if you want, you can also do the stable isotopes of the uncondensable gases, because here you have an enrichment, as I said before, a pre-concentration of the uncondensable gases. Let's have a look at this solid and liquid phase, okay? Basically, we have the liquid phase and the solid phase. We centrifuge to separate the two phases, okay? What we do afterwards? Basically, in the liquid phase, as I said before, SO2 dissolved to form different sulfur species in solution. So we can take this liquid and we can oxidize this solution with H2O2, is a strong oxidizer. And basically all the sulfur species related to SO2 are going to form sulfate. So this sulfate, and we will see later on, can be used to do the sulfur isotopes in SO2. This is quite important. What about the solid phases? We have separated the solid phases. We know that here we have cadmium sulfide that is related to H2S. We are going to use, once again, H2O2 to form SO4. So in this way, we have separated H2S and SO2, and both with the H2O2 are oxidized to produce, to be ready to analyze the sulfur isotopes in SO2 and in H2S. Obviously, we do have fumaroles, but also we have a much lower temperature emission, like in this case, we are in the central Italy, La Manziana. You see that it's a strong bubbling, mostly related to CO2. Or you have a very tiny bubbling, like in these sort of pools. You see a lot of bubbles uprising up to the surface. Or you have these beautiful small mud volcanoes, as we have in Italy, where the bubbling is very gentle, very slow. You take a lot of time to fill your gas vial. In this case, we use a very high-tech instrumentation that is a funnel. Basically, it's the same thing that we have seen with the fumarolic system. The difference is basically that we connect our gas vials with a funnel. it is clear that in these cases, since we have a lot of water, since we are at a low temperature, this means that here you do not have SO2. It's going to be scrubbed. What you have, you can appreciate it with the color, you have H2S. So we can do the same procedure to produce the sulfur isotope of H2S. We also have diffuse soil gases, as Fatima knows very well. It is a typical accumulation chamber, and that allows to measuring the flux. In most cases, the CO2 and methane flux. You can do some small variation that in the accumulation chamber, you can put a sort of small tube with a three-way valve that is connected to a syringe and connected to a gas vial. So basically, you may suck the gas from the accumulation chamber and transfer this gas into a gas vial that is equipped with a rubber septum. Okay, you basically fill this gas vial with the gas. Obviously, this gas vial was previously pre-evacuated. In this way, you may analyze delta 13 of CO2, delta 13 of methane in the accumulation chamber. We are at the interface between the soil and the atmosphere. Maybe that below in the soil or even deeper portion of the soil, you may have a different amount of CO2 and methane in terms of concentration. Maybe also the isotopic composition can be different. If you do not have a lot of money to buy the accumulation chamber system, you may use a static chamber that has the same, basically the same problematics as the accumulation chamber has. Basically, you may do the analysis or the flux of methane, benzene, toluene, and so forth, because you collect the samples at different time, and so you can see how the concentration tend to increase. And on the top of the static chamber, you can put a syringe and use the same gas vials as we have seen previously in the accumulation chamber. So we may suck basically the gas from the static chamber and we transfer the gas into the gas vial. In this way, we can do delta 13 in CO2, delta 13 in methane, or if your equipment is very strong, you can do other kind of isotopes, for example, in the hydrocarbons. Obviously, it depends on the concentration you have in the gas, in the soil gas that you are analyzing. Finally, you can also do interstitial gases in the sense that I want to see how the concentration and the composition of the isotopic composition of the gases is changing with depth, because obviously at the surface you have a strong interference with the atmosphere. So in order to avoid the interference with the atmosphere, you may put inside the soil a stainless steel tube at different depth. Usually, in our case, we use 20 and 50 centimeter depth. And in this way, we may suck the gas by using a sort of gas analyzer that allows you to analyze directly the concentration of CO2. And when the CO2 concentration is stable, with the three-way valve system, you may trap, once again, the gases into the gas vial, as we have seen previously. And here you can do the delta 13 CO2 and delta 13 methane, but also other gases, for example, H2S and so forth. The last part about the gases is related to the dissolved gases, because if you are not so lucky to have a free gases, but you can work with water, because each water may have some dissolved gases inside the water itself. And as you know, for example, a river or a lake is in equilibrium with the atmosphere. So basically, according to the partial pressure in this case of the atmosphere, you have a certain amount of different gases that are dissolved in the liquid phase. As the pressure increases, this means that also the amount of gases in the water tend to increase, okay? And this is typical when you are dealing with thermal waters or with cold waters that have found a strong CO2 emission at depth. So it depends on the partial pressure, the amount of gas that you have inside. So at constant temperature, the amount of this gas dissolved in the liquid is proportional to the partial pressure of the gas in equilibrium with the liquid. And this is the typical Henry's law, where P is the partial pressure of a specific gas, C is the concentration into the solution, and KH is a constant with a unit of measurement of a pressure divided by a concentration. And this basically is the way, it is a law that we use to analyze, obviously, the dissolved gases. We know that the solubility of the different gases is a function of the pressure. And you have much more soluble gases or less soluble gases as a function of the partial pressure. There is another important parameter that is the temperature, because as you know, the higher the temperature, the less soluble are gases, as you can see in this picture. You have methane, oxygen, and so forth. You can see this, their solubility is decreasing as the temperature increases. And this is an important point. But we skip this problem because basically we do the analysis at lab temperature, at ambient temperature. And this is what we do. Basically, we use a big gas vial, pre-evacuated. Our equipment is 250 mils big, pre-evacuated. So when open the valve, there is a sort of decompression, and the decompression allows the water to enter the, the gas vial. Obviously, you must be careful that to avoid to full completely the gas vial, because otherwise you cannot do any analysis, obviously. So usually we fill by 2/3 the volume of this gas vial. And then we can do the analysis, the chemical analysis in the headspace of the exsolved gases during these exsolution processes. So we can do the delta 13 CO2 or other isotopes. Here there is a problem, because when you are doing this sort of stripping, some of CO2, some of other gases are still in the liquid phase. This means that if you want to calculate the concentration or the isotopic composition of the different gases, you need to do a correction. And sometimes the results are not very good. So usually it's better if you use another system. Basically, you fill the water, you fill this container with the water, you close it, you clamp with with a special device, and this lid is consisting of a rubber septum. Then in the lab, basically you displace with the nitrogen, with argon, with helium, a gas that you are not interested with for the chemical and isotopic composition. You displace part of the water, and so you have on the top an enrichment in the gas phase related to the exsolution of the real water that you sampled. And then you collect the gas from the headspace and you do the analysis. So this method is much better than the other, because here basically you do not have any correction. In the other case, the correction might be very, very strong. 2 words about the water sampling. Even in this case, as you know, you have a lot of different water emergencies: thermal water, well water, lakes, dams, river, springs, seawater, and so forth. Important is the rainwater. we will see an example. And inside the water, you have tons of compounds, different compounds from the major, main, and trace elements. And even in this case, as we have seen before for the gas phases, it's clear that these compounds, these ions, cannot be derived by a single source. So even in this case, we may have a water, gas, rock interaction processes that basically results in the chemical and isotopic composition that you collect at the surface. So water isotopes are important for the fumarolic gases or volcanic gases, but are also important for the water itself, because, as you know, we have a strong isotopic fractionation of the rainwater when you collect the water at close to the sea or at very high altitude, because the isotopes becomes lighter and lighter as we move from the coastal area to the inland, let's say. And what you get a sort of diagram like this. Here you have several thermal waters from central Italy, and you can see that are related to the global meteoric water line or the Mediterranean meteoric water line. This means that all these waters, thermal waters, here you may see the temperature, are related to rainwater. So the source of this thermal water is the rainwater. There are some differences. These are the oxygen and hydrogen isotopes from the steam of Larderello, from the famous geothermal field. And you can see that you have what is called the oxygen shift, basically. You have a displacement of the oxygen isotopes, whereas the deuterium doesn't move. This is due to the interaction at temperature higher than 150 degrees between the host rock and the geothermal fluid that produces this displacement. In other cases, when you are in volcanic area, you may have a picture like this, where the steam from different fumarolic gases are not parallel like in Larderello, but they have the straight line that goes to a box that Giggenbach and Taran call andesitic water. And you can see these are steam from different volcanic system in the ring of fire, where you have a subduction related volcanism. So they call this andesitic water. So you may understand that water isotopes are quite important to define the origin of the processes that produces that kind of isotopic signature. Two words about rainwater. Rainwater, obviously, you collect rainwater after a week, after 2 weeks, after a month, according to the precipitation. And if you collect the water in a cylinder like this or in a bottle like this, obviously that you may have evaporation. You avoid evaporation by adding basically a lighter liquid like glycerin. So basically, when it rains, the water enters the glycerin, and the glycerin is a sort of lid. Basically, it does not allow the evaporation of the water. So you can do safely the water isotopes in the rainwater. Okay. For the other waters, it's very simple. For the condensate, we have seen before. For the water, you take the water, you fill a bottle, 50 mils are enough to do the water isotopes. Total dissolving organic carbon, you know this diagram that is related to the carbon species, and the carbon species are related to the pH, because according to the pH of your water, you may have different species in solution. Here, these are not the absolute values, are relative values. Carbonic acid, bicarbonate, and carbonates. And according to the pH of your water, you may see that you have bicarbonate or a mixture between a bicarbonate and carbonate, or if you are in the case of acidic water, you have carbonic acid or CO2, okay? And this is the meaning of the total dissolved inorganic carbon. Basically, the inorganic carbon is the sum of these three terms, where CO2 with asterisk is the sum of a carbon dioxide and carbonic acid. Then we have the concentration of bicarbonate and eventually the concentration of carbonate. What can we do with this important basic chemistry? We can do the carbon isotopes in the total dissolved inorganic carbon, and usually there are two different approaches, where both of them are pH based. What does it mean? That you may exsolve CO2 from your water, or you may precipitate the dissolved carbon by using a salt. In the first case, we need to lower the pH. So this means that we are going to use vials with pierceable rubber septum, where about 2 mL of anhydrous orthophosphoric acid has been added. Then you pre-evacuate, and basically in the field with a syringe, you inject 2 6 mL of your water according to the amount of estimated dissolved carbon, inorganic carbon. Okay, this means that the pH goes down to 1, and you have the release of CO2. And then in the lab, you analyze the CO2, whose carbon is related to the total dissolved inorganic carbon. In the other case, the precipitation, you need to increase the pH. So basically, you add sodium hydroxide pellets, and to increase the pH up to more than 10, then you add strontium chloride, and you have the precipitation of strontium carbonate. Then you filter and you analyze the strontium carbonate, and the carbon of the carbonate gives you the isotopic composition of the total dissolved inorganic carbon. So in the first case, CO2 forms. In the other case, strontium carbonate precipitate. We finish this talk with the isotopic analysis of sulfur in sulfates and in sulfides. For the sulfate is relatively easy, because basically you add some calomel in order to kill all the bacteria, particularly sulfate reducing bacteria that may alter the real isotopic composition of your sulfate. In the case that you want to do sulfur isotopic in sulfate when it's at very low concentration, let's say rainwater, you need to pre-concentrate the sulfate by using ion exchange resin like this one that is reported. And then we're going to add barium chloride. So barium chloride produce a reaction between barium itself and sulfate to forms barythene, basically, okay, whose solubility product you may see that is very low. So this means that the precipitation is very rapid. If you want to reduce the isotopes, the sulfur isotopes in the reduced species, the procedure is a little bit different, because you have to prepare this solution. You see that cadmium is always present. You add in the lab a couple of mils of this solution. So when you add the water, the pH goes up to 10 or more. This means that when you are adding the water, sulfur, cadmium sulfide is going to precipitate, as we have seen for the gases. So we have the solid formation of cadmium sulfide. Okay, you may use this technique or to analyze the sulfur isotope into the sulfide, or you may use this approach for removing the sulfide from the solution where you want to measure the sulfur in the sulfate. Okay, this is quite important. The procedure is, if you want to do the sulfur isotopes in the reduced sulfur reduced species, you oxidize with H2O2, and then you let precipitate the sulfur barium sulfate, as we have seen before. Last slide, why we selected cadmium. Zinc is less expensive, is less toxic, but it has a not very good solubility product. You can see that is -4. Silver is much more, cost more, but the problem is that tend to react with chloride to form silver chloride. So we skip it. You can see that the solubility product is very, very good, but we had to skip this one. The same problem we had with tin and copper, because both these metals, the chalcophile elements, have the co-formation of hydroxide, despite the fact that the solubility product is quite good. We skipped the mercury and arsenic because, as you know, are very toxic, but you can see that the solubility products are very, very good, -53 and -54. We used cadmium because cadmium is a little bit toxic as well, but has a very good solubility product, 10 and -29. So you have the immediate precipitation of cadmium sulfide. Thank you very much. I was a little bit too long.
Thank you, Orlando. So if anybody has any questions for Orlando, just unmute your microphones and you can make the question.
Can I start with a question just to break the ice?
Yes.
Orlando, it's not exactly about the isotopes, but it's about one of the other gases, that is the carbon monoxide. Based on, you said it was tricky. We don't analyze it here in the Azores, but I've been involved in a project and this has been highly discussed. What is the best to measure in the dry or in the soda? It's in the dry. I think most of the community agrees with that, because just to just help me to understand this, more time it passes, of course, if you are measuring in the soda, you will decrease the final concentration.
It's time dependent because the CO tend to react with the sodium dioxide to form formate. You are losing basically.
And we now all basically, I think, use the sodium hydroxide, but some in the past, mostly in Iceland, used potassium. In this case, also, there was a reaction. It was the same.
The same.
Okay.
I mean, you know, there are, according to the different geochemistry, everyone has his their methods.
Yeah, exactly. That's crazy.
Keep the potassium because the impurity are much higher than the sodium hydroxide.
Okay.
It will be the same, just the impurity are a little bit higher.
Okay. Okay. Yeah, this is what I thought about the carbon monoxide, but I just wanted to confirm with all your experience, because as I told you, we don't have. And this is really relevant because at the end, a lot of geothermometers are used based on the carbon monoxide. And this is why you may have differences in temperature from 300 degrees to 100 degrees,
Exactly. No, it's a tricky. Carbon monoxide is very tricky. In the past, we used to do with the soda vials, but we realized that the amount we measured were less than the real concentration. So we passed, it's about 10 years that we passed to the dry gas. The results are much more reliable.
Okay. Thank you.
Welcome, Fatima.
I really like the presentation, just to say.
Thank you. Thank you very much.
Thanks, Fatima.
Thank you for the presentation. May I ask a question?
Yeah.
Yes.
About this use of cadmium hydroxide. How critical you think the selection is between cadmium hydroxide and zinc acetate? Because zinc acetate is what I've been using all the time, because it's like cheap. You can easily use excess of zinc acetate, and also it's not that toxic as cadmium. Of course, you won't have the nice yellow color.
Yeah, no, it's not for the color. It's not for the color.
Yeah, I know you showed this, but how critical you think? Is there really some evidence of isotopic fractionation, for example, related to use of zinc acetate instead of cadmium hydroxide?
Two reasons. The first one is the solubility product, because as I show you, and you may see here, it's just 10⁻⁴. This means before you have the precipitation, you need time. The reaction must be quick, because otherwise, into the solution, as I showed at the beginning, the products related to SO2 and H2S are the same. So if you wait quite a long time, you may have the precipitation also of those sulfur species related to the SO2 as not to H2S. The other point with acetate is that in the soda gas vial, you cannot do hydrocarbons, because if you add the acetate, basically you cannot do hydrocarbons. And sometimes hydrocarbons are important, for example, for geothermometry. Okay, methane, for example, is important for geothermometry. So if you use acetate, you can forget the hydrocarbons.
Yeah, so, yeah, of course. But if we take like just a specific sample for sulfur isotopes, then that's not the problem.
We never tried to with the zinc. We never tried because our target was mostly the fumarolic gases.
Yeah. I'm working with the deep groundwaters, so that's a little bit different environment, and therefore it might be that's also the reason for the selection and the difference between the two.
Maybe I don't know. So obviously our target was different. So we tried to find a sort of a compromise between the different chalcophyte elements. And cadmium, despite the fact it's quite toxic, in fact, when we are preparing this cadmium hydroxide, it's always a little bit tricky, a little bit dangerous, because it forms a sort of white smoke, like when the Pope is done. Yeah, the smoke is toxic. So when we do the cadmium hydroxide, we must be very careful. But it's much better than arsenic and mercury, obviously.
Yeah.
You may kill it yourself with these two guys.
Yeah, I have also used silver nitrate traps, but
silver would be good, but you have see. Perhaps for your purpose is okay. For us, no, because basically you have the formation of silver chloride.
Okay, well, thank you.
You're welcome.
Any other questions? If no, I would like to thank Orlando for the presentation